Time is the only thing you can't see, can't touch, can't stop, and yet it controls everything you've ever done. What if I told you the past isn't really gone? The future might already exist. And right now, this very second, you're trapped inside a paradox your brain was never designed to understand. You know, most people think time is simple. The clock ticks, the day passes, yesterday is gone, tomorrow hasn't happened yet. End of story. But physics doesn't work that way at all. The deeper we look into the universe, the stranger time becomes, and the more it starts behaving like a trick rather than a rule. Now, I don't want to confuse you with complicated equations right away, because the funny thing about the time paradox is that you already feel it in your daily life. Think about this. The future can change what you do today. The past still controls your decisions, and somehow you're standing exactly in the middle of both. That's not just philosophy. That's a real scientific puzzle. What makes this even more fascinating is that the universe itself doesn't clearly tell us which direction time is supposed to go. At the level of atoms and particles, the laws of physics work almost the same whether time moves forward or backward, which means the thing we call the flow of time might not be a fundamental law at all. It might just be something our brains created to make sense of reality. So in this talk, we're not just going to ask what time is. We're going to ask something far more dangerous. What happens if time isn't what we think it is? When you stop and think about it, the way we experience time is really curious. You wake up in the morning, have your coffee, go to work, and by the end of the day, it feels like time has passed. We talk about the past, the present, and the future as if they are distinct entities, flowing neatly from one into the other. But what if this flow is not really there? What if the passage of time is something that only exists in our minds, like the feeling of motion when you watch a movie? It's easy to imagine that a second on your clock ticks away uniformly for everyone in the world, like a metronome. But in reality, the universe doesn't keep time that way. The fundamental laws that govern matter, energy, and light do not require a direction for time. If you filmed a collision of particles in a lab and played it backward, the laws of physics would still be satisfied. Nothing would break. The particles would behave just as they should, obeying the same fundamental equations, whether time is moving forward or backward. And yet, we never see broken cups reassemble themselves or spilled coffee leap back into the mug. Why is that? The answer is not in physics alone, but in statistics and probability. Systems tend to evolve from order to disorder because there are far more ways for things to be messy than neat. This is what gives rise to what we call the arrow of time, the sense that time flows from past to future, even though the underlying rules themselves don't care about the direction. Our minds latch onto this arrow because it's consistent with our everyday experience, but it's not a fundamental feature of reality. In fact, if you look closely, the flow of time is almost a trick of perception. Our brains are constantly recording events and making a narrative out of them, stitching together cause and effect, storing memories in a way that feels sequential. You can think of your consciousness as a movie projector, playing a film in a linear fashion, even though the film itself, the universe, might not have a linear order at all. When we try to step outside ourselves and imagine time without this subjective flow, it feels strange, almost impossible. But that's exactly what scientists do when they analyze the universe at its deepest level. They strip away the comfortable illusion and ask, does time really pass? Or are we just along for the ride? Understanding that the flow of time might be an illusion is not just a philosophical curiosity, it's a doorway into deeper insights about the nature of reality. Once you entertain the idea that past, present, and future might coexist in ways our intuition cannot grasp, everything changes. The way we think about causality, memory, decision-making, and even what it means to live in the now. The illusion of time's flow is like a magic trick that your mind performs every second, convincing you that the world is moving in a simple, straight line, when in fact it may be far more intricate, mysterious, and utterly fascinating than you ever imagined. When we think about time, we often imagine it as a straight arrow. The past is behind us, the future is ahead, and the present is a thin line cutting between the two. That's how we live our lives, and it feels natural, almost obvious. But the laws of physics don't see it that way. At the level of particles, atoms, and fundamental forces, there is no built-in before or after. Newton's laws, Maxwell's equations, even the equations of quantum mechanics all work perfectly whether you run them forward or backward. If you filmed a billiard ball bouncing around a table in a vacuum and played the tape in reverse, the motion would still obey the laws of physics. Nothing breaks. No rule is violated. So why then does time seem to have a direction? Why do we remember the past but not the future? Why does a glass fall and shatter but never spontaneously reassemble itself? The answer is not in the microscopic laws themselves, but in the collective behavior of large numbers of particles and the concept of probability. In physics, the idea that systems naturally move from order to disorder is called entropy, and it provides the arrow of time that we experience. A single particle doesn't care about forward or backward. A room full of air molecules bouncing in every direction overwhelmingly tends to go from a neatly arranged state to a messy, disordered one, because there are far more ways for it to be messy than neat. Entropy gives us the direction of time, even though the underlying rules don't. It's like rolling dice. The chance of getting a perfect sequence over and over is tiny, so we see randomness dominate. But the laws themselves don't prefer forward over backward. They are indifferent. This means the arrow of time is emergent, not fundamental. It arises because of the statistics of large numbers of particles, not because of the core equations that govern them. And this distinction is crucial. It tells us that what we perceive as time's flow is more a feature of collective behavior than a law of the universe. It also opens the door to strange possibilities. In certain exotic situations, such as in black holes or the very early universe, the relationship between entropy and time might behave differently, which could challenge everything we think we know about cause and effect. Some physicists even speculate that, at a fundamental level, time itself may not exist as a separate dimension, but is instead a bookkeeping tool for tracking correlations between events. That's why when we study time through the lens of physics, it becomes less like a river and more like a map, a structure we impose to make sense of events, not a universal conveyor belt dragging us from past to future. Understanding the arrow of time as emergent rather than fundamental forces us to question what it really means for something to happen before or after. It shakes the foundations of causality, challenging the idea that the universe has a preferred direction. And yet, for all its strange implications, it doesn't mean the world is chaotic. It simply means that what we see as time's arrow is a natural consequence of the statistics of complexity, a reflection of the overwhelming tendency for order to dissolve into disorder, and a reminder that our intuition about time might be playing a clever trick on us. Most of us live our lives thinking of the past as fixed and the future as uncertain. Yesterday is set in stone, tomorrow is a mystery, and today is all we get to play with. That's the story our minds have been telling us for centuries. But physics and a little thought experiment can show that this neat division may be an illusion. Imagine for a moment that time is not a simple line, but more like a landscape, where past and future coexist in a strange, intertwined geometry. At the quantum level, particles don't behave like tiny billiard balls traveling along clear trajectories. They exist in a haze of possibilities, where multiple outcomes can coexist, and only when we observe them does one outcome crystallize. This isn't just weird science fiction, it's reality confirmed by countless experiments. If the universe at its core allows multiple potential outcomes to exist simultaneously, it suggests that what we call the past might not be entirely locked in, and the future might already be influencing the present in subtle ways. This is called retrocausality, the idea that future events can affect past events, at least at the level of quantum particles. It's mind-bending because it contradicts everything our brains assume about cause and effect. Yet experiments like the famous delayed choice quantum experiment hint that particles seem to know about measurements that haven't happened yet and adjust their behavior accordingly. If this is happening in the microscopic world, could it have echoes in the macroscopic world we inhabit? It's a big leap, but the concept forces us to rethink how rigid our notions of past and future really are. Even outside quantum mechanics, relativity teaches us that simultaneity is relative. Two observers moving at different speeds might disagree on the order of events. One person's yesterday could be another person's tomorrow, depending on their frame of reference. This implies that the separation between past and future is not universal. It depends on how you move through space-time. When you combine these ideas, the strange behavior of particles, the relativity of simultaneity, and the role of observation, you start to see time as a flexible construct rather than an immutable sequence. The past might be more fluid than we think, and the future might already cast a shadow over the present. It's as if the universe is a movie being played in multiple dimensions at once, and we are watching just one thread at a time. This doesn't mean you can go back and change history like in science fiction stories, but it does mean that the boundary between past, present, and future is not as solid as we imagine. The collision of past and future is a subtle, almost imperceptible effect in our daily lives, yet it's a real phenomenon at the frontiers of physics. Understanding it forces us to question the very nature of causality, to admit that the universe may be stranger than our intuition allows, and to embrace the paradox that while we feel time moving forward, in the deepest sense, it might not be moving at all. One of the most astonishing revelations about time comes not from philosophy or thought experiments, but from Einstein's theory of relativity. You see, time is not some universal clock that ticks the same for everyone, everywhere. Instead, time is flexible, like a rubber sheet that stretches and compresses, depending on how fast you move or how strong gravity is where you are. Imagine you are in a spaceship traveling near the speed of light. From your perspective, everything inside the spaceship seems normal. Your coffee pours, your heart beats, your clock ticks. But for someone back on Earth watching you zoom past, your clock appears to tick more slowly. Seconds for you might be hours for them. This is time dilation. The faster you move relative to someone else, the slower your time passes compared to theirs. It's not science fiction. It's a real, measurable effect. Scientists have verified it with atomic clocks flown in airplanes, with satellites orbiting the Earth, and even in particle accelerators, where subatomic particles live longer when moving near light speed than they do at rest. Time is not absolute. It's relative to your motion. And that's just the beginning. Gravity also warps time. The stronger the gravitational field, the slower time moves relative to a weaker field. Near a black hole, time practically stands still compared to someone far away in empty space. This means that two identical clocks, one on Earth and one orbiting high above, will disagree over time because Earth's gravity is pulling more strongly on the one at the surface. You might think, well, these effects are tiny and only relevant to astronauts or particles moving insanely fast. But actually, we deal with this all the time without realizing it. The GPS system, which guides billions of devices around the world, has to correct for both velocity-based and gravity-based time dilation. Without these corrections, your directions would drift by kilometers every day. Time is not some fixed river. It's a landscape, bending and stretching depending on how you move and where you are. And the implications are profound. It means that the now you experience is not the same now someone else experiences, even if you are looking at the same clock. It challenges our intuition about simultaneity, cause, and effect, forcing us to accept that reality is more flexible than our senses suggest. You might even imagine scenarios where astronauts traveling at near light speed return home to find that decades have passed while they experienced only months, a concept that seems almost paradoxical but is entirely consistent with physics. Relativity teaches us that time is personal. There is no single universal tick-tock for the universe. There is only your tick-tock and mine, intertwined and bending, depending on motion and gravity. It's a humbling reminder that our ordinary experience of time as steady and uniform is a tiny slice of a far more extraordinary cosmic truth. Time is not a backdrop. It is a participant, bending and stretching with the fabric of the universe, making the world stranger and more fascinating than most of us ever imagine. Quantum mechanics has a way of making you question everything you thought you knew about reality, and time is no exception. At the microscopic level, particles don't behave like tiny billiard balls traveling in predictable paths. They exist in a cloud of probabilities, where multiple outcomes coexist until a measurement collapses them into one reality. This simple fact opens the door to some of the strangest paradoxes about time. Take, for example, the famous delayed choice experiments. In these setups, scientists can decide how to measure a particle after it has already passed through an experimental apparatus, and the particle's earlier behavior seems to adjust retroactively. It's as if the particle knew what would happen in the future and changed its past behavior accordingly. It's not magic, it's quantum mechanics, and it has been repeatedly confirmed in the lab. Then there's the concept of entanglement. Two particles can be separated by light years, yet a measurement on one instantly influences the state of the other. If the timing of the measurements is arranged cleverly, it raises questions about which event caused which. At first glance, it seems to violate causality, but the mathematics works perfectly, even though it defies our everyday intuition about time and cause and effect. And consider superposition. A particle can exist in multiple states at once, meaning that from a certain perspective, the past itself may not be fixed. Only when we observe it does it settle into a single history. In other words, the history of a quantum particle can be influenced by measurements made after the fact. These phenomena challenge our classical understanding of time as a one-way street. In the quantum world, time becomes a more fluid, probabilistic concept, where the future can reach back to the past, and the past can be less definite than we imagined. Even time travel, which is usually dismissed as science fiction, becomes a serious thought experiment in this context. Certain interpretations of quantum mechanics suggest that multiple timelines might coexist simultaneously, each branching based on different outcomes of quantum events. This is the foundation for the many worlds interpretation, where the universe splits into countless parallel realities with each quantum decision. From this perspective, time paradoxes aren't paradoxes at all. They're natural consequences of a universe governed by probability rather than certainty. What's fascinating is that these effects are not just abstract mathematical games. They have practical implications for emerging technologies like quantum computing and secure communication, which exploit the strange relationships between particles and time to perform tasks impossible in a classical world. Thinking about quantum time paradoxes is humbling. It forces you to accept that our perception of cause and effect, past and future, may be nothing more than a convenient illusion, a story our minds tell to make sense of a universe that operates according to rules far stranger than we can directly perceive. Time at the quantum level is not a river. It's a dance of possibilities, collapsing, entangling, and unfolding in ways that make the universe not only mysterious, but endlessly fascinating. When you start exploring time as physicists and philosophers do, you quickly realize that it's not just a scientific problem. It's a deeply philosophical one. Because if the past is not fixed, the future is not set, and the present is slippery, then what does that mean for us as thinking, choosing beings? We like to imagine that we have free will, that our choices matter, and that the world is a chain of cause and effect, where one thing leads naturally to another. But the more you examine time, the more those assumptions start to wobble. If, at the quantum level, future events can influence the present, or if multiple timelines coexist simultaneously, then the universe is far less deterministic than we are used to thinking. That doesn't mean we are powerless. It means that the universe is more creative than we thought. Philosophy and physics collide here because we are forced to ask, what does it mean to act in a world where the past and future are not rigid, where cause and effect are probabilistic rather than absolute? Our everyday decisions may feel linear, but the deeper we probe, the more we see that they are part of a complex web, a network of possibilities rather than a simple chain. This changes the way we think about responsibility, about memory, and about experience. Even morality starts to look different when time is not a strict arrow. If events are not fully determined, then every choice carries potential consequences in ways that are subtle and interconnected, beyond what we can immediately perceive. There's also the question of identity. If the future can affect the present, and if the past is not entirely fixed, then who are we in this flowing, flexible timeline? Are we the same self from one moment to the next, or is identity itself a narrative that our minds construct to make sense of events? Some philosophers suggest that the experience of now is really just a convenient fiction, a story our consciousness tells to navigate a universe that does not operate in linear time. And then there is the wonder of it all. Realizing that time is not what it seems opens doors to awe. It tells us that the universe is stranger, more beautiful, and more intricate than we could ever imagine. The solidity of yesterday and the uncertainty of tomorrow are not flaws in the world. They are features, reflections of the deep, elegant rules underlying reality. Thinking in these terms, you start to live differently. You notice that every moment is precious, that each choice might ripple in ways you can't see, and that your life is part of a far grander pattern of interwoven possibilities. Time becomes not a jailer, but a playground, a canvas for curiosity and exploration. And in the end, that is the lesson. Understanding the philosophical implications of time is not just about science. It's about how we live, how we think, and how we imagine our place in the universe. The paradox of time teaches humility, wonder, and the boundless potential of human curiosity, reminding us that the universe is stranger than we ever dared to dream, and we are lucky enough to experience it firsthand. So where does all of this leave us? After wandering through the illusion of time's flow, the arrow of entropy, the strange collisions of past and future, the warping of time by motion and gravity, the quantum oddities, and the deep philosophical questions, one thing becomes clear. Time is not what we thought it was. The neat, linear narrative we live by every day is just a comfortable story our brains tell us. The universe doesn't tick in a single direction. It doesn't care about our schedules, our calendars, or the way we slice past, present, and future into neat compartments. Instead, it dances in probabilities, bends under gravity, stretches with speed, and plays tricks at the tiniest scales. Understanding this doesn't make life meaningless. It makes it fascinating. Every moment is richer, every choice more intricate, every event connected in ways our intuition can barely grasp. The time paradox is not just a puzzle for physicists. It's an invitation for curiosity. It reminds us that the world is far stranger than our senses suggest, that the past might not be fixed, the future might already exist, and the present is a fleeting, miraculous intersection of possibilities. So the next time you watch a clock tick or feel a second slip away, remember this. The universe isn't just moving you through time. It's inviting you to explore it, to question it, and to marvel at its mystery. And if there's one lesson from all of this, it's that the adventure of understanding time is never ending. The more you learn, the more you realize that reality is far more wondrous, far more flexible, and far more beautiful than our everyday experience allows. That, my friends, is the true paradox of time. It's everywhere, it's impossible to hold, yet it's the most incredible playground the universe has given us.